Spatial data contained within a geographic information system is encoded using a geographic coordinate system. Therefore, with this shapefile that we are looking at of country boundaries right now, every vertex along the border of every country is encoded using a geographic coordinate system within that shapefile. The most common geographic coordinate system is the simple latitude and longitude coordinate system with which you are probably already familiar. Latitude and longitude tell us how far a given location is in angular degrees from the equator and the prime meridian, respectively. And many geographic coordinate systems used within the GIS environment use latitude and longitude as the primary mechanism for encoding coordinates in spatial data files. However, some datasets use different coordinate systems. Some use other geographic coordinate systems, and others use completely different units or projected coordinate systems that involve complex mathematical transformations. GIS software is typically very good at handling coordinate systems and converting spatial data from one coordinate system to another. When we loaded information into ArcGIS, for example, when we loaded these vector shapefiles that we are looking at now, every one of those files has a coordinate system associated with it. The unit of the first coordinate system that you load into any document will be specified here on the lower right corner. So because we first loaded a file that stored data using decimal degrees, that is what we are seeing as the unit listed on the lower right corner of the page. Typically, the coordinate reference system, meaning the geographic coordinate system used by the entire document, is also assigned to be that of the first coordinate system that is loaded from a file when we load a file into a map document. If we open up the properties for a layer, we can see what coordinate system is used to encode the data in that layer. If we go to the Source tab here for the countries layer, we can see that the coordinate system is GCS WGS 1984. That again is the most common geographic coordinate system for small-scale reference mapping data, the kind that we see here, particularly when it covers a global extent. There are other coordinate systems, and there are other coordinate systems that use different datums, but the WGS84 coordinate system is very common for mapping global data like the ones that we see here. So actually all of the data that you are receiving for this unit's assignment is encoded using the WGS84 coordinate system. Because WGS84 uses the degree as the angular unit, the actual contents of the shapefiles store latitude and longitude values as the vertices for all of the features that we see here. Nevertheless, if we want to transform the view that we are seeing here into that of a different coordinate system, ArcGIS will allow us to do that. If we particularly look here at the United States, you'll probably notice that the appearance of the United States looks a little bit vertically condensed. The same is true of all of the other countries present within the dataset, and it becomes more extreme as you move toward northern latitudes. This is because the WGS84 coordinate system is a simple geographic coordinate system rendered onto a Cartesian coordinate plane, if you draw it as such. Think of a Cartesian coordinate plane simply as graph paper. If on your graph paper you use the grid to define a coordinate system with an origin point, we would have something very similar to what we see here. Essentially, the points for these countries are being rendered on a Cartesian coordinate plane based on the coordinate values, where we have decimal degrees just being rendered on that linear coordinate system as is. While that gives us a general approximation of the shapes of the countries, given the distortions that are involved in transforming a three-dimensional reality of the Earth to a two-dimensional coordinate space, there is significant distortion introduced when we just plot the coordinates on a coordinate plane as such. Therefore, in many cases, to improve the appearance of our maps, we want to use projected coordinate systems that involve applying complex mathematical transformations to our data in order to improve the appearance, particularly when mapping certain regions of the world. Fortunately, ArcGIS contains a robust database of coordinate systems, many of which are projected, and those coordinate systems allow us to, in many cases, very easily refine the appearance of our map without having to undergo significant effort in order to make that happen. So let's start by just looking at a couple of global coordinate systems that are very common. To change a coordinate system in ArcMap, all we have to do is open up the data frame properties and then go to coordinate system. Note that WGS84 is indicated right away. If we want to look at projected coordinate systems rather than just geographic coordinate systems, we could open up that folder and then navigate down to World. There are many different options here, and I'll apply several of them so that you can see the differences. One common map projection is the Mercator projection. It is a cylindrical projection that is conformal, meaning it preserves shape within the entire extent of the map. However, this preservation of shape comes at the significant cost of distorting surface area. The Mercator projection is one of the most common in its use for worldwide reference mapping, but it is significantly and fairly criticized for highly exaggerating the sizes of features in more extreme latitudes. Many school children in the United States who grew up in an era where Mercator projection maps lined the walls of most classrooms will probably remember seeing how large Greenland is and being surprised to learn that Greenland is actually 13 times smaller than the continent of Africa, despite the fact that it appears of the same size when using the Mercator projection. So the fact that this projection preserves shape throughout the entirety of the world does come at a significant cost. And that comes back to the point that no single map projection can reflect the three-dimensional reality of the Earth in two dimensions without in some way distorting some properties of the geometry. There are other projections that we use for different purposes as well. Again, note that applying a new projection to the entire document is as simple as opening up these data frame properties and choosing a new projection from the list. One of the most popular coordinate systems for mapping the world is called the Robinson projection. If I click on Robinson and hit apply, you'll see why. It gives us a nice elliptical representation of the surface of the Earth, and it introduces some distortion, but not too much. Robinson is referred to as a compromise projection, because what it does give us is a nice visual representation that meets aesthetic criteria, while not actually preserving any geometric attribute perfectly, like shape, surface area, or direction. There are many other worldwide projections available, and I encourage you just to experiment with them. See the differences when you apply different projections. Some look a little less conventional than others. But nonetheless, we can learn a lot about how different projections are used just by experimenting, because one thing that's important to note here is that by simply changing the data frame projection, you are not actually modifying anything in the document, aside from the coordinate system that all of the data are being temporarily rendered as. Changing the data frame projection does not change the underlying projection of any of the underlying data, so you are safe to modify the data frame coordinate system as you like to experiment with different looks. As I've already mentioned, different coordinate systems are better for mapping different parts of the world. If we look here at the Robinson projection, for example, we'll see that if we would zoom in on North America, that doesn't give us a very good look. It's better for mapping phenomena worldwide rather than mapping directly in North America. If we wanted to apply some projections that were better for mapping localized areas, we can do that as well. Note that instead of opening up the World tab here, we could simply find some other options like Continental. We could choose North America, and then we could choose a projection called North America Lambert Conformal Conic. We will just allow this transformation to take place. And then if we zoom in here on just the United States, we can see that this is a very common look for a reference map of the United States. This projected look where we see what is actually on the surface of the Earth a straight line for the 49th parallel, it appears curved because of the conic surface that this projection is using. There are many other projections that would be suitable for North America as well. But experimenting with different projections, again, is very important, and when you are making maps, you will note that projections of one part of the world are often very unsuitable for use in another part of the world. If we take this North America Lambert conformal conic and map Europe, you will see that because of the conic developable shape, we have rotated the land masses of Europe by almost 90 degrees. We could, on the other hand, pick a projection that would be much more appropriate for continental Europe. We could choose a Europe-Lambert conformal conic. And again, we'll allow that coordinate system transformation. In this case, it's not so important because we're not concerned with precision of coordinates necessarily. But when we choose that conic projection, we can see a much more attractive look for the general European continent. So it's really simply a matter of finding the coordinate systems that are best for your given area. If you are wondering which coordinate systems are best, the best thing to do is just do some general research. First, see if you can find appropriate looking projections just by category or name within ArcMap. If you cannot, then you will want to look on some online resources and see what people recommend for a projection for a specific region or country. Note that even most countries have their own country-specific projections that are ideal for mapping. So this projection of Spain for all of Europe looks pretty good, but there are some projections that are designed to, if we wanted to map a specific country, allow us a much better view just of that country. So we could search here for Spain. And we can see that there is a projected coordinate system that is meant to highlight Spain and give it a look that puts it front and center without a lot of rotation or distortion. So again, just searching within the interface is recommended as a first step for finding an appropriate projection for a given area. Note that we will go into much greater detail about projections later on. We will focus upon how to reproject data when necessary. But for the case of simple visualization and mapping, the best thing you can do is always make sure that you are using an appropriate projection by searching through suitable projections in the data frame properties.